All right, so we're going to talk about errors, which is everybody's favorite topic. And so Taylor's theorem, and we're looking to do some error analysis. So let's say I'm going to use this series here, 1 plus x squared plus x to the third plus dot, 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 plus x to the n plus dot, dot, dot. And I'm going to use this to equal. Do we remember what is r here? It's not EGX. X, right? So the series here is infinite, is 1 over, is equal to 1 over a sub 1, let's try this, a sub 1 over 1 minus r. So what's a sub 1 here? 1 over 1 minus x. Okay, now, when we looked at this a little bit ago, we said that this was a very good approximation for this function over a certain interval of convergence. And that occurred when, I'll put IOC over between -1 and 1, because the absolute value of x had to lie between, or less than 1, so the x had to lie between -1 and 1. But what happens if I just use part of this series to approximate this function, 1 over 1 minus x? Meaning, so let's use the first 6 terms. So if I say that this is equal to f of x, and I'm going to say f of x is going to be approximately 1 plus x squared plus x to the third plus x to the fourth plus x to the fifth plus x to the sixth. What have I done? I've gotten rid of or truncated part of it. And what's left? I'm going to call, and I should put it in different colors. What's left is called truncation error. It's the part I'm leaving off, which would be x to the 7, x to the 7 plus x to the a plus dot 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 plus x to the n plus dot dot dot. And is this in and of itself its own series? It sure is, and it's also geometric. So I could say that the truncation error, now truncation is a big word for I lopped off one end of it, right? So the piece of it is gone. Truncated, it's gone. This is a series in its own right. And so what does that equal? What is its a sub 1? X to the 7th over 1 minus x, because it's r, it's still x. So I have a formula for the exact error. The exact error of using how many terms only? I guess we're using the first 7 non-zero. So I can even tell you what my error is going to be. So that's nice. That's if you have a geometric series. Okay? What if you don't have a geometric series? I should write this as geometric. What if we have the general have it centered at A. I can say that f of x is equal to, what is our formula for it centered at A? It would be f of A over 0 factorial plus f prime of A over 1 factorial times x minus A plus f double prime of A over 2 factorial times x minus A to the second plus, and now let's do the nth one. The nth derivative evaluated at A over n factorial times x minus A to the n plus, I'm going to call this the remainder, where this is my Taylor polynomial. Of what degree? Yep. And then this would be my remainder. Does that make sense to everybody? If I use a Taylor polynomial at its nth degree, and then whatever's left will be my remainder. I think that makes sense. Lagrange said that this remainder this is the Lagrange error bound. It's going to lie between, which means I'm doing this, because remember, that's less than, which is between. What's the next term here? So it would be the n plus 1 derivative evaluated at A, but we're going to use some value C. We'll talk about that in a minute. Times x minus A to the n plus 1 all over n plus 1 factorial, and we're going to make this a positive number here. Where have we seen C before? So I'm telling you that the remainder is going to be, if R is going to 0, right, because that's what we want it to do, because all of these, if they're going to converge, have to be going to 0 as n gets bigger and bigger. This is the n plus 1 derivative. Is that a function in its own right? It is. Does it have any maxes or mins? So the error is going to be at least, and I call this m. I replace this with m, where m is defined, and this is a little bit different in the book, as the maximum value of the f of n plus 1 derivative between x and a. So we're going to use the very next term to help us out with that. And Lagrange said that you're going to have your remainder lie between the plus or minus of that. Now this remainder is also going to be of degree n because this is degree n. It's the n order n remainder because it's from the n degree polynomial. Okay? So why does all this matter? I want to find the cosine of x. And we know what that is with the series. What would that series be? It would be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot 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 plus negative 1 to the n x to the 2n over 2n quantity factorial. Let's say I wanted to approximate. This is centered where, by the way? The cosine of something close to 0. The cosine of 0.1. Point 1 is close to 0. What is the interval between 0.1? Well, it just would be 0 to 0.1. But I don't want to use all the terms. Let's just use the first. You want to use the first 2 or the first 3? Okay, Kyle says 3, you say 2. I can't go 2.5. Let's just do 2. Let's do 2. Okay, we're going to approximate using the second degree. What are we going to call it? Second degree Taylor polynomial. Okay, well, so we're going to say that the cosine of 0.1 is approximately. What are we going to do with that? We're going to take 0.1 and stick it in where? X's. So this is going to be 1 minus 0.1 quantity squared over 2 factorial. 0.1 squared is, that's 1/10 squared, which is 1 over 100. And so this is going to be 1 minus 1 over 200, which turns out to be 199 over. Someone get on the calculator for me? What is it? 1.995. Okay, so when you type in cosine of 0.1, what do you get? You got to be Raz. Is it that?
No, 0.5004.
What is this one exact? Can I have more decimals? Is that what exact? Okay. And then the actual, when I say actual, this is going to have on the calculator, which was it? 0.99500 416. So, see?
5278.
We have some error, I guess is what I'm asking you. How do we find the error?
Subtract.
I like that, subtract. And I'm going to do this. Because it doesn't matter which we actually do. So I'm going to say this is going to be 1 minus 0.1 quantity squared, right, over 2 factorial minus the actual, which is what? Cosine of 0.1. You know where we get this from? The calculator. Can somebody give me that number? Can I have all the zeros at this second?
I got 0.5 zeros in the 419.
1, 2, 3, 5 in front here, and then a 4. 1, 6, 5, 2, 7, 8. That's, we expect that we did, don't we? Okay. Well, would it be nice if I could look at the error as a function of x? What would that be? Minus? Right? So, you know where I'm headed, right? I would love it if you helped. So what we're going to do is we're going to say y equals, take a polynomial, and you can follow along in your calculator because you need to be able to see these functions. So y equals absolute value, which is down here at the bottom.
I got it. I have it.
Is it working? Oh, okay, sorry. Okay, we're going to say 1 minus x squared divided by 2 factorial.
The whole thing over 2
Yeah.
factorial? Or just that term?
2 factorial.
Can you factorial in the calculator?
Yeah, absolutely. Factorial is, I think, diamond such that bar. You'll have to tell me if I'm right. Or division. Diamond division. Help me, is that right?
Oh, yeah.
Diamond division?
Oh, yeah.
Okay.
Okay.
What?
It doesn't have a 12 mark on it.
Right, it doesn't. Okay, so go arrow over once there, Jake, and then go minus cosine of x. Okay. So that's the error function. Where is it a good approximation? Yeah, let's zoom in here. Between -1 and 1, right? But gosh, it's really good between, I mean, it's almost, we can almost distinguish between those points. So that's pretty good. What do you suppose happens? Can you copy this and do the control C, right? And then put that into the second one, and then we'll add another term. So this will be plus x to the 4th over, oh well, yeah, over 4 factorial. All right, so let's see what happens when we zoom out a little bit there. Is that even better? Now this is the error function. So what's happening is it's really good. It's a really good approximation near the center, outward to -1 to 1. But it's even better. It's beyond 1 to 1 here from negative. Doesn't it look like it? Even better. Where is it bad? Away at the edges of the interval. Okay. So that's error, basically. So let's say I wanted to find where the error was less than, well, 0.1, because I didn't need to 0.01, because I didn't have to be that exact. We were pretty exact. Like our error was 0.0, you said 0.50. So could I get there with fewer terms, I guess, is what I'm asking. Well, I only have one more term left, so this might not be the way to do it. But does everybody see how do we get there with the error? The error function, how do we create it, is what I'm asking. You get the Taylor polynomial. Right. So to create the error graph, that's going to be the absolute error is going to be equal to the absolute value of it. It's going to equal the Taylor polynomial. I'm going to just put n. Is that all right? Because whatever degree you want, polynomial minus f of x, whatever your function is that you're approximating. And since it's absolute value, does it matter which way you go? It doesn't matter. So let's put in what our actual error was back into the Desmos here. We said it was y equal, didn't we? Said it was point, you said with 5 zeros in it, so let's put y equals 20 or 0.1, 2, 3, 4, 5. You have the digits, right? Do you have the digits still?
I think that's what it was.
And it was 4165.
Yeah, I didn't do, no, I didn't do percent. I just had this error.
Oh, no, I want that. But there were more digits. I don't remember what they were.
4165.
Yeah. Okay, so let's zoom in a little bit. Well, not a little bit. It's so good, we can almost not even distinguish, can we? So what happens if it's not that good?
Our error is very large.
Well, error's going to be bigger, clearly. But could we find out if we wanted the error to be less than 0.01? Let's write y equals 0.01 in the next line, and y, Okay, do you see where we could probably, if you, no, the other way, I'm trying to, you see where it intersects the curve here, the red one?
Yeah.
Let's figure out what that intersection point is. I don't know if it's going to let us do that. I guess it does. So you could say, and let's go to the positive interval and see if it matches. It was 0.7.
No,
It won't stick unless we ask it to turn it over here. That's it. So I can use two terms and be accurate to 0.01 until I get to 0.7028. Yes, ma'am.
What does the 0.7 represent?
I can be as far away from 0 as 0.7028 and the error be less than 0.01. You see? That's pretty cool. Yeah.
So you're saying you could have plugged in cosine of, actually, no.
Yeah, let's do that. Let's do that. Cosine of,
Is it 0.7?
yeah.
Okay, yeah.
And you'll be right. Anything below 0.7026 will be at least that accurate, right? That makes sense, everyone? I think that makes sense. So how do we find what the approximate error is using Lagrange? I'm going to take a picture of this first. Lagrange said my error is going to be at least I need to put space in here. You guys got to calculate on the calculator to get you awake. You're snoozing, Mitchell.
It's
Just right.
straight over. Mitchell, wake up.
Right. So Lagrange said that the error or the remainder is going to be at least the n plus 1 derivative evaluated at c, x minus 0, right? Because my x minus 0 was the center, n plus 1 over n plus 1 factorial. And in this case, our interval is from 0 to, we said, 0.1, right? Because that's where I'm estimating. Okay, but I said that this right here was the maximum of the n plus 1 derivative that we used. We used the second degree Taylor polynomial, didn't we? So what's the next non-zero term? It's going to be the fourth. If you think of cosine, we said that that was 1 plus x squared over 2 factorial. Oh no, it's minus, sorry. Minus. 1 minus, and it's plus x to the fourth over 4 factorial plus dot, dot, dot. What's the next term that we lost? It was this x to the fourth, wasn't it? So I want the maximum of the fourth derivative function. So what if the cosine is f of x? What is f prime of x? Negative sine x. F double prime of x is negative cosine x to triple prime sine x. The fourth derivative. We're back to cosine x. Now, think about that function in its own right. Between 0 and 0.1, it looks like this, right? I mean, so what's it doing? It's decreasing, isn't it? So what is the maximum y value in that interval? Between 0 and 0.1. Everybody agrees 1? That's the worst it could be. The worst error is going to be where this derivative has the highest value, which is 1. So that's what goes here. So n, what we're going to say is 1. And our second degree remainder error then is going to be less than 1, which is the max interval, and then I'm going to say times x, but what is x? Point right. Times 0.01 to the fourth over 4 factorial. So somebody do that on the calculator. What do you get? 0.0000. It's the second, yeah, because we used the second. We used the first two, didn't we? In our polynomial. Okay. This was the Taylor polynomial that we used. Has somebody got me a number? I'm sorry, say it again, Lydia, louder.
0.00000416.
5 zeros?
Yeah.
4?
1, and then 4 is continuous 6. I think 2006, yeah.
It goes on.
Yes.
You're saying that's the maximum error. Now, so what did we get before? What was our maximum error before? Is that less than this?
This that we got before was less than that.
Yes. So Lagrange said that's your error bound. That's going to be the worst case scenario right there for your error. That's pretty darn precise, isn't it? So what did we do to get that error? We looked at the first, the n+1 derivative that we used, which was the fourth. When I took it, this was the first, second, third, fourth derivative. I figured out what that function was, what the maximum error could be between 0 and 1, and it turns out the highest value this is 1. And then I take the x, and where I want the approximation, I raise it to the fourth. And actually, should we put in here? This should be a 0.1, shouldn't it? And then we use Lagrange's formula there to find the error, the bound of the error. That means the error has to be between negative 0.000041666 and the negative, right?
If you were finding it for the third polynomial, like for x of
The third,
for x to the 6 over 6.
if we use to the fourth, and then we had to find it using the n+1 derivative non-zero, we would say this is to the sixth, then what derivative would we need here? We need the sixth derivative, which would be the fifth derivative, which is negative sine x, the sixth derivative, which is negative cosine x. And so let's look at that graph. That's going to be -1, but this is absolute value. Right, so it'll be 1. This is absolute value up here. So I just didn't do it because it was positive here anyway, but you know, it would be absolute value. So you use 1 again, and then it would be 0.1 to the 6th over 6 factorial. Okay? And then, yep.
Can you spend one again to go to 6 for these things?
She wanted, what happens if you use, she said, what if you use these, and then you wanted the error bound for the, if you use this Taylor polynomial, the fourth degree, and you use the 6th, right? And could we calculate, this is an approximation for what the worst error is going to be, the Lagrange error bound. What is the exact error? The exact error is going to be and that's if I'm using that polynomial, it would be error, I can't spell it, equals the Taylor polynomial that we used, which would be 1 minus 0.1 squared over 2 factorial plus 0.1 to the 4th over 4 factorial minus cosine of 0.1. Now, do we expect it to be even better here? I do. So this would be the exact error. What would the exact error be? You're going to have to help me with that. I can't do that in my head. Well, maybe, you know, no.
We match the power, the
Yes.
power to the derivative.
Yes,
So if it was
you do, because that's how we created these Taylor polynomials, right? The 4th degree term is going to be the 4th derivative over 4 factorial times x minus a to the 4th. Somebody give me a number for this?
1.38864.
I'm sorry, what is it?
1.38864 times 10 to the 50.
Oops. Times, which is
Small.
8 zeros.
That's funny. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 8, 6, 4. Right, that's the exact. What would the approximate be? What would Lagrange tell us the bound is? We would say the fourth, right, because we use the fourth of 0.1 is going to be less than, the maximum is going to be, again, 1 times 0.6, or 0.6, 0.1 to the 6 over 6 factorial. So let's see if that is a little bit bigger than this. Because this is the actual.
It's like 1.38 repeating times 10 to the 9.
So this is slightly bigger, right? So Lagrange says it's going to be at least that. Or no, it's going to be less than this. And the exact is a little bit less. But is this a really good approximation, though, for that error? It is. That's why Lagrange uses that error. Because it's nice and easy to calculate, okay? What if we wanted to, an alternating series, all you have to use is the very next term. That'll be a nice error bound for that. So I need you to try the homework, and we'll come back and we'll discuss it. I expect that we'll do a lot of discussing. I understand that, I get that. But I wanted to share with you Euler's formula.
Euler's has a formula, it's something around.
Because this is a famous formula. And it starts with e to the x, and I hope you do that. This is 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus x to the fourth over 4 factorial plus dot 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 plus x to the n over n factorial plus dot dot dot. What if I wanted to plug in e to the xi? Ooh.
Oh, I understand.
I've suddenly left Realville.
Why would we go
Well, this is interesting.
Like, is I is X or is I a different?
I is root negative 1.
Okay.
So what do we do here? We get 1 plus x xi plus xi quantity squared over 2 factorial plus xi cubed over 3 factorial plus xi to the 4th over 4 factorial plus xi to the 5th 5 factorial plus so on and so on. So let's simplify this a bit if we can. This will be e to the xi equals 1 plus xi. What happens when you square I? You get negative. So this is going to be x squared over 2 factorial plus, this is going to be x cubed, I cubed. I cubed is equal to negative I, right? So this is negative x to the third I over 3 factorial. Plus, then I'm going to get x to the 4th, I to the 4th, it's just 1, that's nice. Plus, x to the 5th, I to the 5th. I to the 5th is just I over 5 factorial to the e. She's very loud. And then it would be minus x to the 6 over 6 factorial plus dot dot dot. We agree with that? So let's kind of separate in here and factor out the I terms. Which ones are the I terms? The odd ones. So I'm going to say this equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot, dot, dot. And then I'm going to factor out an I. What happens when we do that? We get x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial plus dot, dot, dot. What does that look like? What is this? This is cosine x. And this is sine x. So e to the xi is equal to cosine x plus I sine x. And the beauty of this formula is what is e to the pi I?
-1.
Let's plug in pi. We'll cosine of pi plus I sine of pi. But what is pi? Sine of pi? 0. So e to the pi I is equal to -1. And Euler's formula was this: e to the pi I plus 1 equals 0. And what's fascinating about this is this equation includes 5 of the most fascinating numbers in mathematics. What are they? E, I, 1, and 0, and how they're all related. Pretty amazing.
I went to the movie theater and watched figures,
Yeah?
and the formula, they were like writing on the boards and calling like the go, no go.
Yeah.
Did anyone call
Really
you
cool.
that?
Can you do me a favor and,
Your equations on the board are not right.
Does it say stop right there?
I'm dying.
Hang on.